In this video, we'll address the issue on what is stable and what is unstable, right, for robustness. Because robustness is a measurement of stability. But we can say that this guy that tips with a leg like that is also stable. We can say that this guy like that also stable. Alright? Although we know that it's unstable, the robustness is not good. But under what circumstances, what degree does this robustness consider unstable? We know that if we have a person that push him down, alright, then he will fall down straight away. He's not robust. Alright, if I have this person that stands maybe somewhere like that, then if let's say this person push him, at least he's still somewhat stable, right? Because although his robustness is still there, alright. So we want to know that how much robustness is considered stable and how much robustness is considered unstable. And here we are. And in order to show you how much is considered stable, alright, I'm gonna explain with a reason. Alright, I mean example, I don't know what I'm talking. We have an L0 over here. But this L0, we have an L0 over here. This L0 is this loop over here. It is very nice, very stable. Alright? And then if you were to design this L0, alright, such that so you know that there is a closed loop transfer function, 1 plus GH, for example, closed loop. Alright, we know that if you want to redesign this L0, alright, you can actually add in more components, K, L, alright, okay, maybe add in like GM, something like that. You may add in more system so that you can actually beautify your design, alright. So when you do that, when you do this thing, alright, you're gonna shift this plot, this Nyquist plot. This is Nyquist plot. This whole thing is a Nyquist plot. It's plotting the Nyquist, alright. And therefore, when you shift, you're gonna shift into L. Alright, you're gonna shift into L, and this shifting of the loop, alright, is gonna make the system less robust. Alright, because this point is nearer to -1. Right? This blue color one is real far away from -1, right? But this point is very near to -1 now. Alright? And also I think this is the nearest point to -1, okay? Well, this point is so far away, alright? And therefore we are still considered stable, right? As long as if you don't change the system such that it actually encircle -1, alright, if you do that, then this whole thing is considered unstable based on Nyquist criterion, stability criteria, alright. And you may find this loop a bit weird, right? Why like that? In fact, it's something like that. If you were to go into mirroring, alright, this is from 0 to infinity, this loop, and then this loop is from 0 to -infinity. It's just the same, so they are just drawing one loop only, that's all. Alright, and therefore this explanation is somewhat saying all this. Alright, is that we want to investigate whether the feedback system remains stable after when you change the system or perturb it to the new loop gain L. Alright, this L it's over here, this red color one, okay? I think it's kind of messy now, yeah. Therefore, here we are going to talk about the sufficient condition in order for stability under a certain so-called disturbance or perturbation or changes, alright? And therefore, in this case, what this means is that if you remember L0, okay, L is simply Cp, alright, L is equals to Cp. L0 is also equals to Cp, or in other words, C0, P0. They are in fact two systems. L0 is one system, L is another system. So there are two systems, but let's just put it as 1 plus Cp0. Okay? If you remember, 1 plus Cp0 is what? 1 plus Cp0 is the distance. It's actually the distance from the nearest system from the plot from its plot itself to -1. This is 1 plus CP naught, C naught P naught lah, okay, like that. Okay, I should write C naught P naught. Okay, so this is the distance. As long as this distance, alright, as long as L, the difference between the red color L, as long as the distance between maybe what do I say? Okay, so therefore L is actually this distance, for example. Okay, L is actually this distance, where L is simply 1 plus CP. Alright, this thing over here is what do I mean? Sorry, this should be CP. Alright, this should be C naught P naught. Okay, this L naught is C naught P naught, L is simply CP. Okay, minus. Alright, so CP, alright, is maybe perhaps 2. Okay, and C naught P naught, as you know, is okay, let me put it that in another way. Okay, I think this is pretty much a bit confusing. Okay, let me put it in another way. Alright, 1 plus CP, alright, is simply this distance over here. Okay, there's no doubt about it. Alright, I mean C naught P naught lah. Okay, this L is CP minus C naught P naught. CP is simply the curvature, simply this curvature over here. Alright, it's simply this loop itself. So it's telling me, so this equation is telling us that if I take CP, which is this red line, minus away this C naught P naught, this difference must not be greater than this 1 minus CP. Or in other words, these differences must never be greater than this differences. Right, because if you were to be greater, then this means that you have a greater loop that is going to into -1. Take that as a somewhat of that meaning, right? Hope this is pretty clear. Where omega is a member of the real number, meaning it can be -5, can be 5, can be 0, 5, 2, 3, can be any number and be any real number will do. Okay, so this frequency lah, alright, under this frequency, this understanding should be made known, and therefore this is one of the robustness function, and we have 8, so we have 7 to go now. Alright, and then the next function, if you don't know what the hell is the function, it's just simply all these functions, all this stuffs. Alright, it's just some meaning to it. Alright, is to really tell us how robustness the system it is, and how, yeah, and therefore let's talk about this system. Alright, this don't be intimidated by this. I also feel a bit intimidated just now. Now I finally understand what the function is. Alright, what function 2 or 3. This is just page 2. Okay, this whole thing is a continuation from the previous part. Alright, which is this one. Alright, this is the one. If I were to paste it lah, okay, if I were to copy this, I were to paste it over here, it's exactly the same thing. Alright, this is the condition, same thing as this. Okay, except we have this thing over here. Okay, alright, now the difference is that if I were to divide them by L0, alright, if I were to divide them by L0, why do I want to divide them by L0? That I want to make in terms of a certain percentage change, right? This is the difference between the curvature, right? If you were to take a look in this portion over here, this is just maybe a different color. This is just the difference between two loops, this one loop and this loop, right? This is just the difference. Alright, this particular thing describes the difference. Alright, if I were to divide by a whole thing by L0, this means I'm going to talk about the ratio between them now. I'm going to talk about the difference, alright, this difference in terms of the ratio of L0. Okay, that's the difference between this two CP, or in other words, it's just the distance over here divided by L0 itself. So in other words, if this value increases, this means you are going to be more unstable because your difference is going to be larger, alright, compared to L0. If your if your CP, because it's governed by CP minus C0 P0, if your CP is going to increase, then you're going to be more and more unstable, and this percentage is going to increase. So this percentage actually tells you how much more are you going to unstable, alright? But in certain sense, anyway, I'll just continue first. We say that we divided everything by L0, right? So if that's the case, we talk about the meaning of this one, roughly, and then what is actually this one. If we remember back, this is, if you were to solve for L0, this is actually C0 P0, right? L0 is over here, C0 P0. Alright, if you remember T, the complementary sensitive function is actually Cp over 1 plus Cp, correct? And therefore, you have to go 1 over T, then this means it's just this one, and therefore it's equals to 1 over T0, and that's all. It's just a mathematical system. Okay, and this is just called and this whole thing is just telling us that this is a relative loop gain perturbation. And if you remember back, 1 over T is what? 1 over T is actually Rm. It's the complementary vector margin, right? And higher the better. Okay, something like that. Okay, I really don't know whether is it higher the better or lower the better. Okay, if it's higher the better, then this difference is gonna be very big, right? That's what we're gonna say, and it's gonna be unstable. But anyway, just note that this is this lah, okay? Later on, if I have time, then I'll just touch up on it and think of it. But anyway, this is the Doyle stability robustness criterion, and it's sufficient condition. It's just sufficient means that it is near unstable, yet okay lah, you know, it can be stable, you know, type of thing. We can like, you know, take it as it's kind of stable. Alright, it's near unstable, but it's okay, we can still accept it, something of that meaning. Alright, and instead of having 1 over T0, I said it as omega naught, or W naught, sorry, W naught. Okay, set this as W naught. This is some criteria. Alright, I want certain criteria. If I set this criteria already, then this fraction over here must never exceed my criteria, right? This criteria is must be bigger than these differences. Alright, and this is where I'm setting this, and we call this bounded by the function W1. Or it's actually bounded because you have bound it as W1. Alright, you have just bound it as that. Okay, and it must be stable if this bounded system is smaller than our 1 over T0. Alright, therefore, in other words, the T0, alright, this T0, this is T0, okay, 1 over T0, which is what we have previously said, right, as this one is actually 1 over T0, right, is actually the range from the safest zone to -1. If you understand what I mean, it's just 1 plus CP and then over CP, something like that. Alright, I mean in terms of C0 P0 over C0 P0, if you were to strictly speaking say that. Alright, just the range between them, that's all. Alright, and for W0 is simply to actually allow that, okay, never mind, because I know that at this point this may be unstable. Alright, if my Nyquist plot, if my perturbation cause it to become like that, is unstable, is near to or maybe unstable is because in reality this is unstable. Alright, so therefore I put this as WO, the bounded. So I actually bound my system right here as W0 round. So this W0 is simply smaller than my 1 over T0. Alright, this is just that meaning shown over here. Even though this might not be exactly the meaning, but at least something near there. Alright, and therefore, if any Nyquist plot that goes over this green section is considered unstable already. Alright, so you actually create another circumstances in other words another condition to specify stability. Alright, and therefore this gives a necessary and sufficient condition. So W1, okay, this is actually W1, will give you a necessary and sufficient condition, or in other words a new necessary and sufficient condition to fulfill. Alright, other than the initial primitive one over here. Alright, this initial primitive one is actually the Doyle stability criterion, while W1 is simply building on that stability criterion. Okay, and now if you were to visualize in terms of graph, alright, this graph itself over here is actually 1 over T naught. Okay, it's a low pass. If it's T naught, then it's a high pass, right? If you still remember, but anyway, so therefore 1 over T naught is actually low pass, and therefore this is the cutoff frequency. If you were to move, in other words, if you were to move, maybe I should show you in, yeah, if you were to move, if your plot is gonna go across this black color line over here, right now, okay, if you wanna go across this, then this means that your signal is gonna be decreasing. T is gonna decrease. You're gonna decrease over here. Alright, so this point, alright, this point of time is in fact talking about this Nyquist plot, this loop over here, because it's already looping the -1, for example. Alright, if that's the case that has occurred, talking about this case, then what you mean, because this is simply plotting for 1 over T naught. Alright, if it's talking about 1 over S naught, then it's gonna be a high pass system. So if you're gonna go into this system, for example, this is maybe 10 omega, right? The frequency is 10. So at the particular same time, the frequency at the 1 over S naught, or the vector margin, is at this point right here. Alright, you're gonna have a peak. Alright, if you have gonna peak, then the part that governs the sensitivity function, alright, this is 1 over S, okay, which is equals to Sm, for example. At this point of time, the sensitivity function, if this is big, alright, therefore the sensitivity function will be decreased. Alright, S will be decreased. You know what? Now I just realized that in fact T is a low pass. It's a low pass system. Okay? Therefore this graph is not 1 over T naught, it's just simply T naught itself. Alright? This graph is simply T naught, and therefore this is a careless mistake. Please take note. Okay? So if T is a low pass system, therefore if at this point of time, alright, this I shouldn't have drawn her over here. I should have, oh yeah, this should be high pass. What am I doing? Okay, then okay, we just continue first. Okay, this graph can still be used. Alright, this graph can still be used, and T is using this graph, which is a low pass system. Alright, and as we say that as the Nyquist plot over here exceeds the range, the acceptable range, then you're gonna fall. You're gonna have this point over here. You're gonna have less amount of T. Since you have less amount of T, you're gonna have a you're gonna increase of S over at this same frequency. Okay, because this is high pass, that is low pass. And if you know that T plus S is equals to 1 from the very initial one, if that is the case, if T decrease, S will increase. That's the meaning of that. But how does this affect our system? If you remember back, S is actually deal with the disturbance. If you want to go back to T RS plus SDS minus TNS is equals to Y of S. if you remember the very first part of the video, the transfer function. So if your t could decrease, then you're going to magnify your disturbance, and this is why increasingly large perturbation will actually cause a lot of destabilizes. So you're going to destabilize the system. You're going to destabilize the system. And the size of the smallest perturbation, alright, is simply stating that if your size, if you were to restrict it, instead of this is for t, right? Instead, my perturbation in this case, the range is for w1. Then I have lesser amount before it destabilize. Alright, that's the meaning of that. So at this point, you're going to destabilize. So you're going to destabilize faster than that, faster than the t graph. So this t graph is this one. If you remember that w1 is the one that we represent, right? We say that we want to, in certain reliability fact, this is the w1, although I write as w0, but still same thing. So this has a lesser perturbation compared to this one. So therefore this is simply the w1, and this is the t. Hope this is pretty clear. This is the overall summary, and that now I know that we have a careless mistake over here. T is low pass and S is high pass, and the rest is just, and yeah, this is not a very good video, but anyway, see you next video for the rest of the robustness part.